In this lesson, we're going to have a look at how we model friction within mechanics. Now, we can use something called the coefficient of friction, which in this equation here is represented by mu. And I'll explain more about this equation in a second. So this value mu is what we call the coefficient of friction. And what this is it's basically a constant depending on the materials that are involved in the situation. And the higher your value of mu, or the coefficient of friction, because this uses a Greek letter mu, then the more friction is available in that scenario. Now what this equation means is F, so this is the frictional force, is always going to be less than or equal to mu, which is your coefficient of friction, times R, which is the reaction force or the normal contact force. Okay, so we can model friction using this equation, where mu just depends on the materials involved. And it's not just a value for each material, because friction depends on the two different materials that are interacting. Now, the reason why it's always less than or equal to mu r, I'm going to explain now. So normally if we've got just a block, we're going to apply a force to it. If I made the coefficient of friction 0, so basically there was no friction, when I apply a force, it starts to accelerate away like that. Okay, it just gets faster and faster and faster. Now, if I introduce some friction, so if I make my coefficient of friction 0.7-ish, now what happens when I apply the force is that there's some friction available. So you can see the red F is the applied force, and the black F is the force due to friction on the left. So as you increase the applied force, the friction just acts to meet it. So it's not that the friction is always, say, 100 newtons. It's that the friction can be up to something like 100 newtons. So as you increase the force, the friction acts to try and stop you. But then obviously it reaches this upper limit. And then once you hit the upper limit, that's your sort of maximum amount of friction used up, and then the object will start to move off. So eventually I'll reach a point where it now starts to move off, because now the red F is bigger than the black F, which is friction. I'll show you it again. So you apply a force, friction just acts to try and match it and stop the object moving, but eventually the friction will reach a maximum, and then if I keep increasing F, the object will start to move. So you can see it's bigger and bigger and bigger, and now it's stopped increasing, but I can increase my applied force to make it accelerate. So that's what's going on. So let's look at an example. So a particle of mass 5 kilograms is pulled along a rough horizontal surface by a horizontal force of magnitude 20. Just draw a quick little picture. So it's being pulled along by a force 20 newtons. The coefficient of friction, so mu, between the particle and the floor is 0.2. Calculate the magnitude of the frictional force. So let's first of all find out what the maximum friction is. Now we can either use it as an inequality like before, or we can just say the maximum friction available is equal to mu r. So in this case it's going to be 0.2 times, well, the reaction force here, which is r, is just going to be equal and opposite to the weight, 5g, because there's no other forces acting up or down. So it's just going to be times 5g. So when I calculate this, 0.2 times 5 times 9.8, we're going to obviously get 9.8. So 9.8 newtons, that is the maximum friction available. So when I'm applied a force of 20 newtons to the right, the friction is going to be trying to go against it with 9.8 newtons, because that's the maximum that it can. Okay. Now that I know that, I can work out the acceleration. So resolving to the right, I've got 20 minus 9.8 equals 5a. And then we can find out what a is. So that's 2.04 meters per second squared. Now, part C, what would happen if the applied force is changed to 3 newtons? So we're just going to get rid of these forces here. So instead of 20, it's now going to be 3 newtons. Now, the maximum available friction is 9.8. So what's going to happen is friction will now be 3 newtons as well. It's not going to be 9.8 because imagine if it was. Imagine if friction was always at a maximum. That would mean that when you pulled it with just a small force, it would actually shoot off to the left, which would not happen. That's definitely not what happens in real life. So friction just acts to try and stop the object up to its maximum point. So if the applied force is changed to 3 newtons, then the friction would then be 3 newtons, and it wouldn't move. So it would not accelerate. What would happen if the force was changed to 9.8 newtons? So now this force here is 9.8 newtons, and then the friction would act to stop it, but it would also be at its maximum friction. So the friction would now be 9.8, but that is its maximum. So if you increase the pulling force anymore, then it would start to move. So what we would call this is on the point of moving or on the point of sliding. Okay, this one's very similar. Have a go at this question, maybe pause the video and have a go, and then we'll go through it in a second. So here we've got a similar question. The mass is 5 kilograms. The value of mu now is 0.4, and a horizontal force P is applied to the block. Find the magnitude of the frictional force and the acceleration when P is each of these values. So first of all, when it's 10 newtons. So let's calculate the maximum friction. It's going to be mu times r, so that's going to be 0.4 times 5g, because r in this case is equal and opposite to 5g. That won't always be the case because you might have an external force which is acting vertically, but here we don't. So that's 19.6 newtons. So if this is the case, in part A, if the applied force is 10 and the maximum friction available is 19.6, friction is just going to be 10 newtons as well. So it will just act to stop it. And A will be 0. Part B, if we change P to 19.6, well, that's exactly the same as the frictional force at its maximum. So the friction is going to be at its maximum, 19.6 newtons. A is still going to be 0, but it would be on the point of moving or on the point of sliding. Then part C, if it's 30 newtons to the right, well, in that case, the friction is definitely going to be at its maximum of 19.6, and we can resolve to the right. 30 minus 19.6 equals 5a, then we can find a. 2.08. There we go. Okay. So here we're told that the coefficient of friction is 1/7. Okay, mu is 1/7 in these questions. And here we've got some different external forces which are acting vertically. So what we're going to have to do in these questions is we need to calculate R first. We need to be careful with how we do that. So if I resolve vertically in this question, I'm going to have R minus 14 minus 5g equals 0 if we assume that the acceleration up and down is 0. So R is not just going to be 5g, R is going to be 5g plus 14. So that's 63 newtons. So then the maximum friction is going to be mu R, so that's 1/7 times 63. So the maximum friction is 9 newtons. So in this case here, if the applied force is 6, that would mean that the friction is just going to be 6 newtons, and the acceleration will therefore be 0, just wouldn't move. Okay, the next one. Again, let's resolve vertically to find r, first of all. So I've got r plus 14 minus 5g equals 0, because the acceleration up and down is 0. Solve that to find r. So this time it's going to be 5 times 9.8 minus 14. So that's 35 newtons. So the friction is going to be 35 times 1/7, which is 5 newtons. So this value here of F is 5. So now I can resolve to the right. 6 minus 5 equals 5a. And then a is obviously going to be 1/5 or 0.2 meters per second squared. If we compare the two questions that we've just done, they're all exactly the same. They've got the same mass, it's the same 6 newtons applied. The only difference is if the 14 is up or down. Now, think about this in the sense of things that you know. If you're trying to move an object, maybe you're trying to move some furniture, and in this example, someone sits down on top of it, adding an extra force downwards, that makes it much harder to move. So the maximum friction is 9 newtons. Whereas in this one, this is like someone lifting the table up a little bit, taking some weight off it, and you can see the maximum available friction is now 5. So that makes it easier to move, and then it accelerates off. So hopefully this makes sense of what you know in the real world too. Okay, so the last one. So this time we've got a force lifting it up a little bit, but at an angle. So the first thing we need to do is resolve this force. So this vertical bit here will be 28 sine 30. And the horizontal bit will be 28 cos 30. So we can use those later. So resolving up and down, we've got r plus 28 sine 30, because they're both going upwards, minus 5g equals 0. And we can solve that. 5 times 9.8 minus 28 sine 30, so that's minus 14. So r is 35 newtons. So the maximum friction is mu r, and mu is 1/7. So that's 1/7 times 35, which is obviously 5 newtons. Now we need to judge, is it going to be at its maximum friction or not? And the thing that decides that is the applied force, which here is 28 cos 30. 28 cos 30 as a decimal is about 24.2. So yes, it is going to be at its maximum friction. So this value here is going to be 5. And then we can resolve to the right. So we've got 28 cos 30 minus 5 equals ma. And we can find a. So we get 3.85. Okay, when you've got things like this in terms of trig, it is quite useful sometimes to write them as decimals, just so you get a bit more of an idea about the actual scenario and which force is bigger than which other forces, just to help you think about it. Okay, so we can also combine this with what we did last lesson and combine it with some slopes or some inclined planes. So here we've got a 10 kilo object on a slope, and the slope has got a coefficient of friction of 0.3. And we're going to find what is the acceleration. Presumably it's either going to stay where it is or slide down the slope, one of the two. So we need to just put our forces on as we did last time. So this is 10g. I can resolve that into perpendicular to the slope and parallel to the slope with this angle as 25. So this component here is going to be 10g cos 25. This one's going to be 10g sine 25. We've also got the reaction force here. And there's probably going to be some friction here. I'm just going to label it as Fr. Now, the maximum friction is equal to mu r. To find r, we need to resolve perpendicular to the slope. So looking at the forces perpendicular to the slope, so in this direction here, we can see that r must be the same as 10g cos 25. Or you could write r minus 10g cos 25 equals 0. So this is our value of r that we can use. So the maximum friction is going to be 0.3 times 10g cos 25. Which gives me 26.65 newtons. So that's the maximum friction that I can have available to me. Let's see if it will be at its maximum or not. Let's compare it to this value here, because this is the force that is pulling it down the slope. So 10 times 9.8 times sine 25, that's 41.4. So that's much bigger than the frictional force. So yes, it's definitely going to be accelerating down the slope, and the friction is going to be at a maximum. Okay. So now we can resolve and find out what A is. So going down the slope, we've got 10g sine 25, which is this force here pulling it down, and then minus the frictional force, which I'm going to write as 0.3 times 10g cos 25. So this bit here is basically mu r, or my friction. And that equals ma. So that is 10a. And then we can solve this to find a. We get 1.48 down the slope. Okay. So it is important that you check just some of the values to compare. So here I checked what is this value here compared to this value here, just to tell me is it accelerating up or down the slope. Okay, here's another question. Maybe you want to have a go at this one first. You might want to pause it and just have a go on your own first. So we're told that the mass is 2 kilograms. Oops, let's not draw this in highlighter. So the mass is 2 kilograms, and it is sliding down a rough slope. So it tells us this time that it is sliding downwards, that it is inclined at 30 degrees. Given the acceleration is 1 meter per second squared, find the coefficient of friction. So this time mu is just going to be mu. And that's what we've got to find. So the setup is the same as before. Let's draw our forces on and resolve them. So I've got 2g cos 30 here, and I've got 2g sine 30 here, and I've got the reaction force here. And if it's sliding down, then friction is trying to stop it. So friction is acting up this way. Okay, now you've got to try and resolve this to find out what the value of mu is. So basically trying to find what the friction here is. So if I resolve down the slope, which is the way that it's accelerating, then I've got 2g sine 30, so this force here, minus the friction. And remember, the friction is equal to mu r, and then that equals ma, so that's 2 times 1. Now we don't know what mu is, that's what we want to find. And r we find by looking at the perpendicular forces here and here. Now in this case it's not particularly complicated. You can see that r is just going to be 2g cos 30. If there were some external forces involved, you might have to do a bit more resolving to find r, but here it's just 2g cos 30. So actually I'm just going to replace this r with 2g cos 30. Okay. And I'm just going to solve this equation. So it's going to be 2g sine 30 minus 2 divided by 2g cos 30. That will give me the value of mu. And when I do that on my calculator, I get 0.4595. Let's just write down a few decimal places, 4595, or if I round it, that's about 0.46 for my coefficient of friction there. Okay, so we're going to have a look at one where we do have some extra forces on the slope as well. So here we've got a particle of mass 5 kilograms, and it's being pushed up a rough slope that is angled at 30 degrees by a horizontal force P. Now here it's a horizontal force P, so this force is going into the block and pushing it up horizontally like that, not parallel to the plane. It's going horizontally like that. Given that the coefficient of friction is 0.2 and the acceleration is 2 meters per second squared, and its head is being pushed up, so the acceleration is up this way at 2 meters per second squared, find the value of P. So we're finding this force here that's helping push it up. Now, we're going to do exactly the same things that we normally do. We're going to do the weight and resolve it, and we're going to resolve this force here as well. So let's do the weight first of all, just because that's nice and easy. So that's 5g. Do the same triangle that we do. So that's 30 degrees. This is 5g cos 30. This is 5g sine 30. This is going downwards, and then this one is also going down that way. We've got the reaction force, which is here. Now P, we can resolve this again into parallel and perpendicular to the slope. Make your real force the hypotenuse. That was the tip that I told you last time. So that's the right angle there. So if P is going into the block to push it up, there must be a component which goes this way, and then the other component must go up the slope, like that. Now in terms of the angle in this triangle, notice that we get this nice Z shape, which means that if this is 30 in here, then this must be 30 in here, because P is horizontal, so it's parallel to the bottom. So if this is 30, then this is 30, because they form alternate angles. So we can say that this angle here is also 30. And now we can resolve P. So this force that's going up the slope parallel to it, this is P cos 30. And the force that's going into the slope is P sine 30. Okay. The only other force we haven't got on here so far is friction. If it is accelerating up the slope, then the friction is trying to stop it. So the friction is acting downwards like that. Okay. So we've got all of our information on the diagram, and that's normally the most important thing in these questions. You do most of your working out on the diagram itself. Okay. And try and resolve all your forces before you do any calculating. So now what we've got to do is find out what friction is. So we can use F equals mu r, and then we can resolve up and down the plane. So let's find the maximum friction first of all. So F equals mu r. We know that mu is 0.2, but we need to find r first of all. And r is going to be a bit more complicated to find because of this external force. But we will resolve perpendicular to the slope, so in that direction. So I've got r, which is in the positive direction. Then it's going to be minus p sine 30, because that's going the opposite direction, and minus 5g cos 30, because that's this force here, and they equal 0. Okay, because it's not accelerating in this direction. So I can rearrange this now to find what r is. So r is going to be p sine 30 plus 5g cos 30. So now I can resolve parallel to the plane, and I know what my friction is going to be as well. If it is accelerating upwards, then I think we can assume that friction is going to be at its maximum. So let's resolve up the plane now. So the force that is helping push it up is P cos 30. That's pushing it up the slope. The force stopping it doing that is 5g sine 30. So that's minus 5g sine 30. And we've also got friction trying to stop it. So that's going to be minus mu r. mu was 0.2 and r was p sine 30 plus 5g cos 30. And that equals ma. So that's 5 times 2, because it was accelerating at 2 meters per second squared up the slope. Okay, so you've got the force pushing up, minus the weight, which is trying to pull it down, minus friction, which is trying to stop it. So this whole thing here, this is just mu r. And now we've got an equation which has got only one unknown in it, which is p. So we can then solve this equation to find p. Not a particularly nice equation to solve, but we can solve it to get p. Let's just go through and do that now then. I'll walk you through the steps just in case you can't get there yourself. So p cos 30, that's going to be root 3 over 2 p. And this would be 5 times 9.8 times 0.5. So it's going to be minus 24.5. Then we've got, if we expand this out as we do it, so we've got minus 0.2 times p sine 30. Sine 30 is a half times 0.2. So it's going to be minus 0.1 p. We've also got minus 0.2 times 5 times 9.8 times cos 30. So that gives me, I'm just going to keep it as an exact answer, 49 root 3 over 10. That's what my calculator gave me, and then that equals 10. And now I can solve it. So I can do 10 plus 49 root 3 over 10 and plus 24.5. And then I want to divide that by root 3 over 2 minus 0.1. So I get p equals 16.3 approximately. Which I've just checked, and you don't get that one as an answer. Same equation, let's just do it in a few more steps just to make sure that we do this right. So we've got root 3 over 2 minus 0.1, lots of p on the left. Then on the right we've got 10 plus 49 root 3 over 10 plus 24.5. So we can add all these up. So that's 10 plus 49 root 3 over 10 plus 24.5, and then we need to divide it by root 3 over 2 minus 0.1. So you actually get, yes, 56.1. That's better. Okay. So not necessarily the algebra, which is actually the important bit here. The important bit is basically the working out on this diagram. And in these sort of mechanics problems, what I said before is really true, that most of your working should be on the diagram. And then that makes your work later on so much easier. Don't try and resolve things whilst you're writing equations. Do all the resolving first on the diagram. And draw your diagram nice and big as well. That's always an important tip. Okay, so to practice these, first of all, I've got a worksheet similar to the one that we did last lesson, just slopes, but then with some friction involved. And after that, you can also have a go at exercise 5C to practice these sort of questions.